All right, so the fundamental theorem, Evan basically says this. It basically says that if I can differentiate something, then taking an integral of that is essentially like an inverse operation, right? One undoes the other and vice versa, right? And so based on the relationship, the fundamental theorem of calculus was born. And we've already talked about that if I have a continuous interval, I can take an antiderivative, I can plug in the value of b, I can plug in the value of a, I can subtract those two things, and I can get what's known as a net change, or an area under a curve, okay? So this is not new. Now, guess what we're going to do over the next, I don't know, 2 or 3 days, probably 3 days. We're going to do every variation of this that we can. So Austin, what's going to wind up happening? There's going to be x's up here. There's going to be variables down here. We're going to take derivatives of integrals. We're going to take integrals of derivatives, right? So we're going to take this concept and we're going to turn it every which way inside and out that we can, okay? But again, we'll review the concept that we've already discussed, but we're going to do so with some problems that are going to require some higher algebra skills. Brandon, if I want to do this problem, I want to evaluate the integral from 1 to 3 using this, I'm sorry. I want to evaluate this function as an integral from 1 to 3. What does that process look like? Well, I take the antiderivative of this. I plug 3 into it. I get a value. I plug 1 into it. I get a value. And I do what? And I subtract them, right? So that's exactly what we're going to do here, okay? All right, so some notation things, some things that are going to become important, some things that I've sort of just bypassed as means of getting to a concept. Notation-wise, here's what I like to do. I know that I have to take an antiderivative of ex minus 3. What is that going to give me? It's going to give me e to the x minus 3x. Now, I like putting the antiderivative in a set of brackets. That's just what I do. And then what I do is I do like a line, right? Okay, so Austin said plus c. That would be true if it was an indefinite integral. Indefinite meaning there were no what? No things up here and down here, right? Because there are boundaries, right? And you know what I'm going to do? I'm even going to do this. Don't write this. Well, you know what? Write this down. Plus c. And I'm going to evaluate it from where? From 3 to 1, right? So Austin says plus c. And is he technically right for an indefinite integral? Yeah. So what am I going to do? Well, I'm going to plug in what? I'm going to plug in 3. And when I plug in 3, what do I get? I get e cubed minus 3 times 3 plus c. And then what am I going to do? I'm going to subtract what? E to the first minus 3 times 1 plus c. And what do I get as a final result? Well, I get an e cubed, right? I get a minus e. I get a negative 9 and a positive 3, so minus 6. And Austin, what happens to the c's? They go away, right? So do we see why putting the c there doesn't really matter? It's always going to go away, isn't it? Yeah. So we don't really need that with a definite integral. And so this would be my value. All right, so no problem there, right? We get into a problem like this. And do we really think that we're going to start doing negative half powers and blah, 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 blah? Or are we going to pray the sweet, sweet Lord above that this is a what? It's one of the antiderivatives that we got to remember, isn't it? Now, how is it one of the ones we have to remember? There was nothing with a 2. Well, can I rewrite it as this? And what did I just do? Well, I just created a constant multiplier rule, didn't I? So this 2 comes out in front of the antiderivative of that on that bound, right? So I have 2 times, what was the antiderivative of that one? That was one of our special ones. Sine inverse, right? And that's from 1/2 to 0. Yeah, so this was a nice one to remember, right? All right, so now what are we going to do? Now we're going to plug in the 1/2. We're going to plug in the 0, right? So I'm going to get 2. Oh, wait, hang on a minute. Sine inverse. Guys, here's the thing. Brandon, do you agree that if you had like a reference sheet or something, this would be pretty easy to identify? Yeah, but you got to know it, right? And then the next piece here, this is one of the sine values as an inverse that we should know, right? Because the sine of what is 1/2? The sine of 30 is 1/2. Yeah. Now remember, 30 degrees, we don't do what? We don't do degrees, right? We do radians. So we're going to write pi over 6. And then sine of what is 0? Sine of 0 is 0. And so what do I get? I get 2 pi over 6 or pi over 3. All right, but again, guys, is the calculus on that problem really difficult? Or was it more just like this question right here, guys, more than anything is, did you study? Do you know your crap, right? So do you know this antiderivative? Do you know the inverse of that? Do you know the inverse of that, right? I mean, the actual calculus here is a breeze. This is, do you recognize what I could rewrite this as? So could I do an antiderivative by trying to do a power rule and all that? I could, but I'd wind up with something to the 0 power. That's why this is one of the special cases. Because I can rewrite this as 1 over x. And 1 over x was one of our special cases. Antiderivative of 1 over x is natural log absolute value of x. That's right. And we're going to evaluate this from here to here. Let me try to write that a little smaller. There we go. All right, so we're going to plug in the e squared. We're going to plug in the 1. We're going to take the difference. Now, guys, I'm going to magically just get rid of these absolute value signs. Why is that okay? They're already positive, right? Yeah, they're already positive values. And here's the thing. I guarantee you, there's no question about it, that if this is like a multiple choice question, there is no way this is left as the answer. Because this 2 can be brought out in front using a power rule, right? What's 2 natural log of e? 2. Minus natural log of 1 is 0. Why? Because the same thing is asking what? E to what power equals 1, and it's 0. So 2 is your answer. right? So again, it's not a really difficult calculus problem, is it? It's just like some things that we got to remember, right? And there's a perfect example, guys, of what some AP style questions could look like. All right, now these ones say evaluate using any method, right? So we can do anything we want. I'm going to talk about some special ways that we might do a couple of these problems. Would you be thinking special case here? Or would you just be thinking, let's just take an antiderivative and go at it? I would just do it. Yeah, it's not a really difficult one to do, is it? So I would suggest that the best way is just to go right at the antiderivative. So a third of x cubed minus 3x from 2 to 1. Right? Now again, they're going to expect that you can do this problem without a calculator. All right, so I got to start plugging some stuff in. So it's going to be a third All right, so I get all that. Plugged in our what? Plugged in our 2, plugged in our 1. All right, let's see if we can do this by hand. Order of operations. 2 cubed. 8 times a third. 8 thirds. Minus what? All right, so it's going to be 8 thirds minus 6. All right. 1 cubed times a third. Minus 3. So it's a third minus 3. All right, how am I going to do this by hand? Well, I need to put these together, right? Common denominator would be what? Would be 3. So I would make this what? 18. 8 minus 18. Negative 10 thirds. All right. And then a third minus 3 is what? Negative 8 thirds. Negative 2 and 2 thirds. Fair to say? What is that going to give me? Yeah, so this is going to be what? Positive, right? Yep, because this is negative and this is minus, so 2 positive, so negative 2 thirds. Hey, what can you tell me about this curve between 1 and 2? What does that mean? It's below the x-axis, right? Why? Because the integral was negative. Now, is the whole thing below the x-axis? Do we know? Not necessarily, right? We just know that the sum of the areas, not the sum of the areas, there you go. Yeah, cool. All right. What would you want to do here? Give me something to do first. X to the 1/2. What about the 3? Make it in front. Yeah, let's get it in front. And you said x to a 1/2. All right, so this is probably not going to be a real difficult one to deal with. What am I going to make the power? What's a 1/2 plus 1? 3/2, yeah. So 2 thirds in front because I don't want anything there right now. Good. Evaluating it from 4 to 1. All right, again, these are like, we expect you to be able to do this by hand. So it's going to be 3 times With that, right? This is where knowing, like, Lexi, this isn't really a calculus problem. I mean, it is, but it's just, like, this part right here is just, do you know your math, right? So the bottom is the root, right? The top is the power. So I want to do what? I can either take the square root of 4 and get the square root of 4 and get 2, and then take 2 cubed, 2 and cube it, right? Which is what? 8. Or I could take 4 and cube it, which is 64, and then take the square root of it, which is 8. So either way, you're going to get the right answer. 8 times 2/3. All right, 1 to any power is 1, right? And then this is minus 2/3, right? So that's 3 times 14/3. What's 3 times 14/3? That's 14, right? Now, again, do you guys agree that a problem like this, I can just type in the calculator? Really, really, really simple, right? You guys got the inspires. I mean, this is so easy to do. What was that one from? 1 to 4. So we love this, right? I mean, how nice, right? So yeah, it'll do that for us. All right. This is just one that we what? You just need to know it, right? So we either do or we don't, Evan, right? So this is going to give me tangent of minus tangent of. And again, it's another one of those cases that we either know it or we don't, right? Tangent of 45 is 1. Tangent of 0 is 0. And so we get 1. How do you guys want to do this one? What do you think? Linear. What does an integral really count or calculate? Really calculates area under a curve, right? Couldn't I just, like, like, this is one that we really haven't talked about. So if you're stuck, all right, so what I just drew right here is not the graph. That's that, right? What do I need to do to change this to this? Yeah, so the idea of finding the root, right? And having that be the point where this thing what pops back up, right? Well, what's the root? Where does this cross? At a half, yeah. So this crosses at a half, which means it pops up here and looks like this. Boom, boom, right? And what is this problem really asking me to find? It's asking me to find the area under the curve from here to here. That's not bad, is it? Isn't it just two triangles? Yeah, so I want to know the area from, let's see if we can draw it, highlight it. So I want to know that piece up to here, right? That shaded region. So what do I have? I have a triangle that's how big over here? It's 1 by a half. So how am I going to find the area? 1 times a half, right? Because it's base times height divided by 2. And then this is what? 1.5 by 3. So what do I got? I got a quarter plus 9/4. 10/4. 5/2. Right. So again, any point in the storm, right? We're trying to, I mean, which is why we want to have an understanding, Lexi, of not just the rule of how to find an integral, but what that rule really accomplishes, right? Because there are cases when we just bypass using the rule and just think of it in the other concept, right? And this is a perfect example of that. All right. How would I do this? Find the exact value. I mean, if you look at that thing, guys, it looks complex, but there's a whole bunch of minuses and pluses. Well, minuses in this one, right? So doesn't that just mean I have 3 separate problems in one? Because really, this is nothing more than the integral of this boom, right? That's all it is. And so I could have simply just put example A, B, and C, right? And this looks kind of similar to some of the stuff that we just did in the previous page. Like for example, this right here, right? What do you notice? That was a constant multiplier. And isn't this the same as 1 over the square root of that? So isn't that just the sine antiderivative? Sine inverse antiderivative, right? And this is the same as 5 times 1 over x, right? So there's some hidden things in here, right? Now, immediately, guys, why do I put constants in front? What's the purpose of putting a constant in front? You don't have to include it within the antiderivative e's, right? E's. Why would this one maybe make sense to leave it here when I actually take this antiderivative? Because what's the power going to be? 5, and what goes in front? 2. So it's a really easy one to do, isn't it? In fact, it's probably easier than if I put the 10 in front. Because if I put the 10 in front, the power is 5. Now I got to fool around with fractions, right? Get it? Yeah. All right, so antiderivative, you guys said was 2x to the 5th. All right, so we're going to evaluate that one. Minus. Everybody agrees that I have a constant multiplier here. All right, so minus 2 times. What's the antiderivative of this? Well, we said that's the same as 1 over the square root of that. So it's the sine inverse, right? And lastly, we have what? This is the same as minus 5 natural log of the absolute of x. I gotta do littler ones. All right, so guys, hey, since these are all the same, I can put these all together now, right? And do this all as one problem instead of what? 3 separate ones. You guys agree? Okay. So if I plug in the 1 over e, right? I'm going to plug in the 1 over e here. I'm going to plug in the 1 over e here. I'm going to plug in the 1 over e here. Okay. So let's do it. Actually, before I do it, let's rewrite it as the equivalent. All right. So there's the equivalent. All right. And now we're going to pop these things in. Guys, I'm going to blow your mind with what's going to wind up happening here. You're going to be like, are you kidding me? But, uh-oh, there it is. You're going to be in just, Austin, your mouth won't even be agape. Like this. Agape. That's a crossword puzzle word, agape. It was what? Oh, no. No, it's way too advanced. All right, starting with 1 over e. So I have 2 times. All right, so there's that part. All right, same thing now with the half. What do you guys think they're doing on the wall? What's, again, and I show you this, guys, because to emphasize the fact that the AP Calc exam, Lexi, is not just an exam in calc, right? If you're looking to simplify this, watch how I'm about to blow your mind. Order of operations says that I got to do the 5th first, right? 1 to the 5th is 1. So this is 2 over e to the 5th. Are we okay with that? Is there any reason why we would know sine inverse of 1 over e? No. This right here is I'm about to blow your mind. 1 over e. Could I rewrite that as something else? Okay, I could do that. E to the negative 1, right? Wouldn't this be the same as 5 natural log of e to the negative 1? Because I don't need the absolute value of signs anymore because this is positive, right? Well, doesn't that allow me to take the negative 1 and bring it out in front, which makes it what? It makes it negative. This was a negative, by the way. There we go. So this makes it what? It makes it plus 5, doesn't it? It just makes it plus 5. Anybody amazed by that? Lexi, you are? Then I got 2 over 1/32, so I have minus 1/16. And then I have plus 2 sine of a half. Oh, wait, this is one I should know, right? We said that this was 30 degrees, pi over 6. This is 2 pi minus pi thirds. This is what? This is just natural log of a half. Any reason that we should know that? Minus 5 natural log of a half. Oh, yeah, sorry. Whoop. Plus, thank you. That's my best answer, I believe. Right? So again, it's not so much a calculus problem, guys, right? Well, I think it may have blown your mind a little bit, Lexi. No. No. There is actually, you know what else we could do here? Guys, this is the natural log of a fraction, right? So if I have the natural log of a fraction, couldn't I do this? Natural log of 1 minus the natural log of 2, right? And what is the natural log of 1? 0. So isn't this minus 5 natural log of 2? I could write it that way. All right. I mean, so just little teeny things here, guys, that I just want to sort of remind you of. All right. Guys, what I'm showing you here today is just a bunch of different AP style questions, okay, using the fundamental theorem. This is another perfect example of an AP style question. Find the area bounded. Okay, so as soon as you see area, you know that you got to start thinking about, am I above or below, right? Because that means I might need to flip some things or throw some negatives in. Find the area bounded by this parabola, y equals 0, x equals 0, and x equals 3. So I've given you 4 things to create a boundary with, okay? So let's do that. All right, so here is one boundary. Here's my other boundary. Y equals 0. There's the third boundary. And the curve itself is going to create some sort of boundary. Well, let's pretend this looked parabolic. Clearly my scale's a little, let me fix my scale a little bit. This is a little askew. Hang on. All right, so here's what it says. There's areas bounded by these things. So what do I mean by areas bounded by these things? Is there any enclosed areas that are created using any of these items? Nothing over here is enclosed, right? This piece is enclosed, right? In the little piece, yeah. So I got this, and I got all that, right? Okay, it didn't say above, it said bounded by. It is a boundary, but it's enclosed, but this piece right here closes that in, right? So when it says bounded by, there has to be an enclosure. right? There has to be an enclosure. So if you have an enclosure, then you have a bounded by. No, it's not. This, yeah, it is. This is, but it doesn't matter. So in other words, if my curve looked like this, let's say, suppose my curve did this, right? Suppose my curve did this. So first of all, this would not be part of it because it's what? Outside of the boundary, right? Inside the boundary, bounded by. So first of all, that would be, that's a bad example. Hang on a minute. They're not, let me get rid of that. Let me get out of that. Hang on. Okay. Y equals 0. Why am I allowed to go above it and not below it? Right? So what's going to wind up happening is this. When there are vertical boundaries, right? That's basically going to tell us where my interval is going to begin and end, right? In terms of x value, sort of the domain of the problem in a sense, right? The curve is then going to be bounded by this. So bounded by just basically means, okay, within here and here, is there any areas of the curve that extend either above or below, right? That creates an area. So if I had this picture, let me give you a different example. Suppose I said, here's a dotted, here's a dotted, here's a curve, here's a boundary, right? What you would take in this scenario would be this, this, and that. Is that cool? You got it? Okay. Did you say that was fun? Oh, all right. You'll see why it works that way in a minute, okay? Maybe not in a minute, but over the next course of the couple days. All right, so I'm sorry that you feel that it's dumb, Lexi, but this has a root at 1. And we know that because x squared minus 1 has a root at 1, no doubt about it. Do you agree that I can take an integral from 0 to 1? Tell me about the value of that integral from 0 to 1. It's negative. Why would it be negative? Because this area is where? Below the curve. Below the curve. So here's what I'm going to do. From 0 to 1, if I found that area, it would be negative, right? So I have two options. Option 1. Is I can say I want the negative from 0 to 1 of the integral. Option 2 is to do what? Flip the 1 and the 0, right? So write it this way. Because what will that do? That will negate the value, right? That will negate the value. So you can do it this way or this way, it will work. So that's this little piece right here, right? What do I need to add to that? Everything from 1 to 3. So then I got to add from 1 to 3. I'm not doing anything fancy with that, right? Why am I not doing anything fancy with those? Because it was already what? It was already above the curve. Is this going to be a real tough one to take an integral of? Not at all, right? Should be pretty easy. Which one do you guys want to do? Option 1 or option 2 to evaluate it by hand? You want to do it graphically. How are we going to get an exact area? It's not linear. Which is why I could estimate it using trapezoids or rectangles. So it's all right. It all sort of starts to come together here, right? But we're not going to do it that way, okay? We're just going to do it by hand. And it's an easy one. Now, this also says I can use a calculator, right? Well, how would I put this in the calculator? Exactly the way it looks, right? So suppose we did option 2. From 1 to 0. Boom, right? So we got our solution. Probably going to be 7 1/3. Yeah, probably going to be 7 1/3, right? Seems like it's going to be. So calculator says calculator says 22/3, B. So we'll do option 2. Pretty easy one to take a antiderivative of. A third of x cubed All right, so that's what I got to do, right? And again, guys, you're expected to be able to do this by hand, right? So it's a pain, but we got to be able to do it. Come back. All right, let's see if we can do this here. What do I got to do, guys? I got 2 separate integrals, right? I got to plug 0 into this, plug 1 into this, and take the difference, right? Then I have to add, plug 3 into this, plug 1 into this, take the difference. Guys, see what we have to do, right? 2 separate integrals, right? So I'm going to have a third of 0 cubed minus 0. I need more room. All right, so just to make sure everybody is cool, this piece right here is that integral, right? And then what am I going to wind up doing? I'm going to wind up adding this one. And that part is this. Evan, are you impressed? Me too. All right, so let's see if we can do it. What's this whole thing right here going to give me? That's all 0, right? This is 1 cubed, 1 times a third, 1/3 minus 1 negative 2/3, and that was negative, right? So this yellow gives me 2/3. Plus 3 cubed, cubed, 27, divided by, or times a third, 9, minus 3, 6. All right, so that's going to be 6 minus, we already did this, right? We got 2/3, right? 6 minus negative 2/3, right? What does that give me? Gives me 2/3 plus 6 and 2/3. What's 6 and 2/3 plus 2/3? 6 and what? 6 and 4/3, isn't it? Which is what? 6 and 3 is 18 plus 4 is 22/3. Wow. Evan, I don't know about you, but I'm getting a little excited about how far we have come. This is incredible work right here, if I've ever seen it. Incredible work. Last one that we'll do today, or we'll at least get it going. Find the area of the region bounded by the curves. Y equals 0, this, and this. Anybody want to venture a guess what this thing looks like? Well, what does this thing look like? Looks like one of these, right? So 2 to the x looks, or 2 over x looks really similar to that. And then what did I do to it? I subtracted 1, right? So it takes this graph and shifts it down 1 unit, which the asymptotic nature at 0 goes down to -1. You guys see it? Okay. You kind of got to have an idea what it looks like to do this one by hand, don't you? Kind of, because like in that previous problem, Lexi, what did I have to do? I had to separate it into 2 separate integrals because some was above, some was below, right? Well, that's probably what's going to wind up happening here. So you got to have a basic idea what your curve looks like. So this one essentially is going to look like this. Right? So it's one of those curves that's been shifted down. So there's also an asymptote that already exists here, right? Just by the nature of the curve. Okay? But here's the thing. This curve right here, right? This is not the boundaries for our problem. This is just what this curve looks like. Everybody okay with that? Now, for the purposes of this problem, I want to have a boundary that begins at 0. And Lexi has figured out why that's there. She's figured it out because we're separating it into 2 separate integrals based on above and below. Okay, that's why we're doing this kind of a problem. Then I have one at 1. Let me think about this for a minute. What do I need to know about this curve? What's kind of important to know? Where the thingy is. What's that thingy called? Root. Now, yeah, could we get like all fancy and stuff and set it equal to 0? But guys, I want to know where this thing has a root, which means where is this equal to 0? What value can I plug into here to get this equal to 0? 2. Yeah, because this is -1, so this has to equal 1. 2 over 2 equals 1. So this root is at 2. All right, so the boundary is at 1 and E. The boundary is at 1 and E. So check it out. Is my curve going to have some regions bounded? We have a little piece right here, right? And then we have this little piece right there. I sort of over highlighted all that. Let me try that again. I'm going to have this little piece here and this little piece here. All right. We said that root was at 2, right? So Evan, from 1 to 2, my curve has an area that's above, right? So from 1 to 2, I'm just going to take an integral because I'm going to get a positive answer. But from 2 to E, I need to do what? Where's the highlighted region from 2 to E? Below the curve. So what do I need to do? Flip, either subtract it or flip like this. Right? This one I flipped it, right? So I flipped to negate the integral. Brandon, why did I want to negate the integral again? Because this is what? Below the curve, right? And areas can't be. There you go. All right, we'll stop there, guys.